Okay, sorry student, so I think it's now on mute. So hello my dear, welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in a right direction. I am Pragyabrat Tripathi, faculty department of mechanical engineering. So my dear, today we will start the most excellent question practice. Okay, that is the excellent question. First you tell me, first you know that what is the excellent practice question. Okay, excellent, it is not means that very lengthy question is there. It is not like that. It is like that, that means you have really have some food in, you have to take some food according to your concept. That means these are the food of your mind. Excellent question, that means there is a something we will have to take in the mind so that my mind is strong. So that perspective, it is not very lengthy, it is not very short, it is not very easy, but it should have some quality. Okay, so some quality problem is there. Okay, so we'll start the first problem. What is that, beta? See, a piston cylinder device, there is a piston cylinder device. Okay, no problem at all. There is a piston cylinder device. Okay, beta. So a piston cylinder device contains 0.8 kg of steam. That means there is a steam is there. That means initially in the piston there is a 0.8 kg of steam, right? Okay, and that steam is at a temperature of 300 degrees centigrade. We don't know what is the condition at that point. What is the condition of the steam at that point? We don't know. We'll compare with the table. Okay, and what is the pressure? 1 megapascal. That means in a piston there is a substance, a fluid is there. There is a fluid is there. And what is the fluid condition? The fluid have a total mass 0.8 kg and at a temperature of 300 degrees centigrade. And what is the pressure? Pressure is 1 megapascal. Okay, that means this is your 1000 kilopascal. Okay, this is at 1000 kilopascal. Now steam is cooled. Now the steam we have to cooled up to what level? We cooled 1/2 of the mass condense. That means we have to condense the steam which is present in the piston cylinder arrangement so that it 1/2 of the mass, that means 0.4 kg mass will condense. So how will done? We have to extract the heat from the system. That means we extract the heat from the steam. Up to what level? That in that container 0.4 kg of the liquid and 0.4 kg of the vapor will there. Okay, so which of the following statement is correct? Now this is the MSQ. We have to instance MSQ. So more than one option is correct. More than one option. So in the GATE question it may be asked. Okay, so see, this is your table and this table is the property table of the steam. Directly we have to take a snapshot on the property table of the steam. So in the property table the pressure it is given. Corresponding to that pressure saturation temperature it is given. Corresponding to that pressure saturation temperature is given. And there is a other property like a specific volume of the fluid, F for fluid, a specific volume of the saturated liquid, specific volume of the saturated gas, a specific enthalpy of saturated liquid, specific enthalpy of a saturated gas are given. Okay, so and also it is given at 1 megapascal. This is given with at 1 megapascal. It is given at 1 megapascal. Why? Because it will be at 1 megapascal. The specific volume it is your 0.25799 meter cube per kg and specific enthalpy is 3051.6 kilojoule per kg. This is the specific enthalpy is there. Now, so we have to find the final temperature is, we have to check this final temperature is this much or not. Reduction in volume is, okay, the volume will reduce. How much the volume will reduce? Heat rejection during the process and the final pressure is 1 megapascal. We have to check. Okay, so first we have to draw, my dear, first we have to draw a piston cylinder arrangement. So this is your piston cylinder arrangement. So let's suppose this is our piston cylinder and this is our piston. Okay, this is our piston. Now in this piston there is a gas is there. Okay, this is your gas. Let's suppose in a piston there is a gas is there. Okay, now this gas, this is the piston, it is gas, and this gas have a mass, that means this mass is 0.8 kg. Now if you remove heat from this system, that means heat rejection. Okay, so the part of the steam will condense. So this is your condensed steam. This is your condensed steam. Okay, this is your condensed steam. This is your condensed steam. So the total is 0.8 kg. In that 0.8 kg, 4 kg, this is a condensed liquid. Condensed liquid. Okay, this is your condensed liquid. Now we have to plot a TS diagram. First we have to plot this TS diagram, is very useful. And this is your saturation curve. What is this called? This is your saturation curve, meet at a critical point. This is your critical point. This is saturated vapor line. This is your saturated vapor line. This is your saturated liquid line. Saturated liquid line. Okay, and the condensation will happen at a pressure of 1 megapascal. See, the condensation will happen at a 1 megapascal. That means the pressure it is 1 megapascal. That means 10 to the power 3 kilopascal. Okay. Now, so this is the pressure corresponding to that. This is your saturation temperature. So what is the saturation temperature it is given? The saturation temperature it is given. The saturation temperature it is given at 1000. The saturation temperature is given 179.88. How much? 179.88. So this is your 179.88. Okay, this is given. Now, but the pressure, now beta, it is given the sample. This sample which is given in the initially, the sample it is at 301 megapascal. So at a 1 megapascal, the sample it is here. So the 300 is above that saturation temperature. So the temperature is above than the saturation temperature. That means the sample it is in superheated. Sample it is in superheated. So this is our sample. So this is your 300 degrees centigrade. This is your 300 degrees centigrade. Okay, so this is your 0.1. So this is your 0.1. Now it will start, it will condense. When you have to start the condensation, you just follow this line. So in this process, it will start condensation, reduce temperature, and here it will first drop of the condensation. So here it will, at this point, this is your saturated vapor denoted by G. So at this point, this is first start of condensation. First start of condensation. This is the first start of condensation. Just start to condensed. Okay. Then, now my dear, it will start the condensation, and this condensation, when up to which level? Until 1/2 of the mass is condensed. 1/2 of the mass is condensed. So the condensation will take place and 1/2 of the mass is condensed. So what is the dryness fraction? Final dryness fraction, you may calculate it. So what is the finest dryness fraction? This is very important. Why? Because where is the final point? Either it is at this point or this point or this point, anywhere. So first we calculate the dryness fraction. So dryness fraction is what? Mass of the vapor divided by total mass of the vapor into mass of the liquid. Okay, so mass of the vapor is 0.4 and this is your 0.8. So this is how much? 0.5. So it is just middle. That means the final point is at here. That means this is your 100, this is your 0% of x. This is x is equal to 0 and this is your x is equal to 1. So if we averaging this is your 0.5. So just middle it is at 0.5. So this is just point number 2. So this is our now path. So 1 to 2 is our process. 1 to 2 is our process. So 2 it is in wet region. Where it is? Wet region. This is in wet region. This 2 is in wet region. 1 is in superheated region. Superheated region. This is your superheated region. Superheated region. This is so 1 to 2 there is a process. So beta this, let's suppose this is point number G. So 1 to G the heat will reject. So 1 to 2 there is a rejection of heat. Mind it beta. 1 to 2 there is a rejection of heat. The part of the rejection of heat from 1 to G there is a latent heat. No, sensible heat. Why? Because temperature will change. So in this 1 to 2, the temperature drop is due to the sensible heating, sensible heat rejection. G to 2, there is a latent heat rejection. So the total, if you know about this, what is the heat rejection? What is the heat rejection? So this heat rejection during the process 1 to G plus heat rejection during the process G to 2. So this 1 to G is due to the sensible heat rejection, and this is your latent heat rejection. This is your latent heat rejection. Okay, no problem at all. Now, so what is the condition is there? First point is what? See, the final temperature is, yes, the final temperature is itself in a saturation temperature. Why? Why? Because condensation up to in a wet region, and in a wet region temperature and pressure are coincide. That means it is not changing. Constant is there, okay? So this is true. A is true. That means number A, question number A. A is, what is the T2 temperature? The T2 temperature is T saturation. And what is the T saturation temperature? 179.88 degrees centigrade. So the option A is correct. Option A is correct. Now we have to take the option, any of this one, we have to take the option of this one, no problem. Second one, what is the second one? Reduction in the volume. We have to find the reduction in, so what is the reduction in volume? Reduction in volume, that means final volume V2 minus initial volume V1, and this is the total volume. So if you calculate, why? Because mass is there. So M into a specific volume of 2 minus a specific volume of 1. Now my dear, we have a mass, but and we have a V1. V1 it is given. So this V1 is what beta? V superheat at which temperature? 300 degrees centigrade. It is given. And this V2 is what? This V2 is V2. This is V2. So this V2 is what beta? This V2 is at which pressure? Is at which pressure? 1 megapascal and 179.11 degree. That means this is your 179.88 degrees centigrade. Okay. So V2 is what? VF. Okay. VF plus X2 Vg minus Vf. and this is at this pressure. So this superheated, it is given, yes or not? This is given. How much? 0.25799. 0.25799. So this is your 0.25799. So superheated 0.25799. If you calculate this much, if you calculate this one, so what is VF? VF at 179.88. VF at 179.88. How much? 0.001122. 0.001127. 0.001127. This is VF plus what is X2? X2 is 0.5. What is VG at this temperature? The VG is, this is your VG. VG is 0.19436. 19436. 19436. 19436 minus what is VF? 0.001127. So how much it is V2? So the V2 comes to be 0.09774 meter cube per kg. So this is your V2. So V2 is there and V1 is there. So V2 minus V1 you have find very easily. So what is your V2 minus V1 then? V2 minus V1 is what? M into V2 minus V1. Okay, beta, put this value M. M is 0.8. 0.8. What is V2? V2 you just have to calculate 0.09774 minus specific volume of 1, 0.25799. Okay, if you calculate this value is 0.12819 meter cube. So this is your beta minus. Okay, there is a minus. Why you got higher minus lower? So the minus indicates reduction. So reduction is how much? 0.12819 meter cube. This is approximately 0.1282 meter cube. So I think this option is also correct. Okay, so 0.1282 meter cube. That means B also correct. So option B. So option B is also correct. Now take option C. What is the option C? Option C is heat rejection. What is the heat rejection from point 1 to point 2? So what is the heat rejection? So heat rejection at a constant pressure. The heat will reject. See this, my dear. The heat will rejection 1 to 2. It is at constant pressure. Pressure is fixed. This pressure is fixed. So heat rejection at a constant pressure is what? Is what? Change in enthalpy. Change in enthalpy. So heat transfer at constant pressure is, that means heat transfer at a constant pressure is change in enthalpy. That means H2 minus H1. What is H2 minus H1? M specific enthalpy of 2 minus specific enthalpy of 1. So my dear, what is H1? H1 is H of superheated. At which temperature? 300 degrees centigrade. How much it is given? Let's see how much it is given. 3051.6, 3051.6, 3051.6, 3051.6 kilojoule per kg, I think. Okay, this is given. Now, what is H2 then? How to find H2? So H2 is equal to 2 is in wet region. So HF plus X Hg minus HF. Yes or not? Yes or not, beta? So my dear, this is at which pressure? This pressure is at, your temperature is at T saturation. T saturation. So what is HF at that point? The HF is, what is HF at that point? HF is 726.51. 726.51. 726.51. 726.51. What is X? 0.5. What is Hg? What is Hg? Hg is 2777.1. 2777.1. 2777.1 minus what is HF? 726.51. So how much it is? If you calculate what is H2, H2 is, if you calculate the H2 is 1769.805 kilojoule per kg. So this is your H1 and this is your H2. So what is the heat transfer at a constant pressure? Is equal to mass. How much is the mass? 0.8 into what is the H2? H2 is 1769.805 minus H1 is higher, 3051.6. If you calculate, this is your minus 1025.436. So this is nothing. This is your heat rejection. Why? Because this is a negative sign. This is a negative. So this is how much? 1025.436. So this is the heat rejection. This is the total heat rejection. So this is okay or not? Please check it. 1225.436 is, yes, C is also correct. C is also correct. C is also correct. Now what is the D option? D is the very simple. D is the very simple. The final pressure. The final pressure. What is the final pressure? Yes, it is 1 megapascal. Why? Because the final point is at the wet region. Okay. So final point is it at wet region. The final point it is at. The final point it is at wet region. And which pressure? The pressure is 1 megapascal. So final pressure and initial pressure are same. That means the final pressure, if you write like that, final pressure P2 is equal to P1 is equal to 1 megapascal. Correct? So I think all options are correct. Yes or not? I think all options are correct. A, B, C, D. So like that, this problem may be asked in your GATE examination. So this is why this is the basic calculation. Okay, and from that one, this is little bit how to read the table of the saturation table. How to read the saturation table. Okay, likewise we have to solve this problem. Okay. Now, so we have to go to the next problem. What is that? This is your next problem. Please see. This is your next problem. Please see, beta. This is your next problem. Please see. This is your next problem. What is that? See this one, beta. What is that? The following table of a property was printed out for the saturated liquid and saturated vapor. That means these tables are corresponding to the saturated liquid property and saturated vapor property. Okay. The titles for only the first two columns are available. That means the title. What is this one? So this is your temperature and this is your pressure. First two columns. So this is column number 1, this is column number 2, this is column number 3, this is column number 4, this is column number 5, this is column number 6, this is 7, and this is your 8. So there are 8 columns. Okay. So in the 8 column, that means first 2 column, that means 1 and 2, you know that. What is 1? 1 is the temperature range. What is the 2? The pressure range. Okay. Now all that we know is that the other columns, that means 3 to 4, 3 to 8. So 3, 4, 5, 6, 7, 8. How much? There are 6 columns. Contain data on a specific property. What is the specific property? The property which is divided by the mass, namely internal energy. That means it may be internal energy, enthalpy, and entropy. That means what they want to ask that, beta, they ask that this property, what we have to label. Either this is a specific enthalpy, this is a specific internal energy, this is a specific internal. What is the data is given? This is very good question is there. There is no any concept, only there must be observation is there. So there is a observation is there. Okay. So please mind it, what is the observation for that one. Okay. So in the question, only they ask the specific enthalpy data in the columns. In which column the specific enthalpy is there. But we have to find all the properties. Okay. From column 3 to column 8, we have to find all the properties. Okay. Now, so start with that. Okay. Start with that. Okay. So we have the specific. We have to find the specific. First, we have to find a specific enthalpy. We have to find a specific enthalpy data. Yes or not? We have to find a specific enthalpy data. We have to find a specific enthalpy data. Okay. We have to find. Sorry. We have to find a specific enthalpy data. A specific enthalpy data. See, a specific enthalpy data. Okay. But we have to find all the data here. We have to find all the data here. No, not problem. So what we have to find this, what the column this contain, what this column contain, what this column contain, what this column contain, what is. So before that, we have to a relation. Good evening, Saurabh. We have a relation. What is the entropy? What says the entropy, and what is the enthalpy? That means what is the standard equation? Okay. So if you draw the TS diagram, so on the TS diagram, what is the line is there na? TS diagram. If you plot a constant pressure line, these all are the reversible process. So what we know that for the reversible process, what is the heat transfer? Yeah, you can say that what is the entropy change. So you have a data. So other one is how much is there? So 3, 4, 5, 6, 7, 8. How much is there? Column is there? 6 column. So in this 6 column, what is possibility is that? The possibility is that, okay, sir, there is a specific property SF, SG. This is your specific entropy. Specific entropy. Then you have UF, UG. This is your specific internal energy. Internal energy. Okay. Specific internal energy. Then there is HF and HG. This is your specific enthalpy. Yes or not? This is your specific enthalpy. Okay, my dear. This is your specific enthalpy. This columns. This is your saturated liquid is there. This is your saturated liquid property. Saturated liquid, and this is your saturated vapor. Saturated vapor. Okay, this is your saturated vapor. Now my dear, see what is the entropy? What is the entropy first? So we know that the entropy, that means change in entropy, delta S. Yeah, fundamentally you know that ds is equal to del Q by T. What is T? T is the temperature of a system boundary across which the heat will transfer. This is infinitely a small heat transfer. Now, if you integrate it, so this is what? This is what? Delta S is equal to, this is your integration dq by T. Okay, that means what, beta? This saturation condition, this is the saturation, that means HF, Hg. During the changing, the temperature is constant. That means if you represent this line, 1 second my dear, it is your, let's suppose T and S diagram, and this your saturation curve is there, and let's suppose this is your constant pressure line, and this is your constant temperature line. So in this region the temperature is fixed. So this is your Sg and this is your Sf. So Sf and Sg, if you find, this have a fixed temperature known as saturation temperature. So if you integrate it and you take this temperature outside from the integration, why? Because this is your saturation temperature and this is your constant. This is your constant during phase change. Phase change. Now my dear, this is your delta S is equal to, this is your Q1 to 2, okay, from process 1 to 2, and this is T saturation. Okay, so this SF delta S is what? Sg minus Sf. Okay, and what is Q? This heat transfer. Okay, सिक्स्थ क्लासेस की ऑनलाइन क्लास कब होती है? व्हाट इज दैट बेटा? हाय मोनिस, व्हाट आर यू आस्किंग दैट बेटा? सिक्स्थ क्लास की ऑनलाइन क्लास कब होती है? ओके, सिक्स्थ क्लास की, यू आर इन द सिक्स्थ क्लास, सो यू आर नॉट हियर, आई थिंक यू आर रॉन्ग प्लेटफॉर्म. ओके, you are in wrong platform, Mahesh. Okay, it is not a sixth class, it is your bap of the class, your father of the class. Okay, so it's not your, it's a senior classes. Go the other platform. Okay, so what is that? This is your Q1 to 2. Okay, now what is this? This is the heat transfer at a constant temperature, and also there is a constant pressure. So during that, the heat transfer, it is at a constant pressure, is what? Change in enthalpy. That means this is your Sg minus Sf divided by T of saturated, and this is what beta? This is your latent heat by T of saturation. T of saturation. Okay, that means the enthalpy value must be greater than the entropy value must be greater than the enthalpy value. Why? Because this is divided by T, and this T is the positive quantity, and absolute temperature, this is the absolute value Kelvin. So the change in entropy must be higher than the change in enthalpy. Change in entropy must be higher than the change in enthalpy. Why? Because it is divided by the saturation temperature. So it's have a some value. So if you divide this temperature in the energy, so the value Sf Sg must be less than this value. Why? Because it is divided by some positive quantity. That means Sg, that means Sfg, this is called Sfg, always less than Hfg. Always less than Hfg. Why? Because it is divided by the temperature. Number first observation. What is the next observation? So if you compare the specific enthalpy and specific entropy change, so a specific enthalpy have a higher value as compared to a specific entropy form. Why? Because specific enthalpy divided by the temperature, then we have to get the specific entropy change. So the specific entropy change must be less than the specific enthalpy. Number first. Number second, what is the number second? Number second is that that means this SFG is the minimum value because it is divided by the temperature value. So we can write here, so SFG is the minimum value because its result because it's come out to be because HFG divided by temperature. Okay, so it's a minimum value. So which one have a minimum value? See this one in this table. Which one have a minimum value? Which one have a minimum lowest value? This is, take any one. With respect to this one, this is 88 approximately. This is 0.36. This is 89. These two are approximately same. 5, then 1200, 1200. This is a 1400 approximately. So in this one, this 4 and this 6 have a minimum value. All other than that one. All other the column, the minimum value is 4 and 6. The minimum value is 4. Why? Because entropy is divided. See Vita, this is time and it is plus 273. So this is 273 plus 273 plus 273. So these are the very higher quantity. If this quantity is divided by the any energy quantity, obviously the result is a very minimum. So you select the minimum column. So column 4 and column 5 have a minimum column. Minimum integer value column. So column 4 and 6 have minimum value. This is your minimum value. Okay, this is your minimum value. So this is now. So which one is higher? SG always higher than SF, yes or not? TS diagram. See the TS diagram. Specific entropy of a saturated gas is higher than the specific entropy of a saturated liquid. So this is a minimum. So this is the maximum value of S, and this is your minimum value of S. So which one is SG and SFC? Minimum. These two are minimum. These two are the minimum. Why? Because it results come out to be when there is a divided by temperature. Now in the minimum, SG is maximum as compared to SF. So in the minimum, SG is maximum. So for the minimum, SG is maximum. So here, see this one. This is entropy. Okay. So in this entropy, SG is maximum as compared to SF. So this 6 is SF. This 6 is SF, my dear. This 6 is your SF. No, SG. Okay. And this 4 is SF. Why? Because SG always greater than SG. SG is always greater than the SF. So that this value is maximum. So this column are specific saturated a specific entropy. That means this is a specific value, a specific entropy. So this is the specific entropy of a saturated gas. This is the specific entropy of a saturated liquid. Okay. 2 column done. Now remaining 4 column. So we have to take a next step. This is the first for the entropy concept. Now we have to take the next approach. What is that? See my dear. What is that? See my dear, what we know that? We know that, see this one, from here you cannot. We know that, what is the enthalpy? The enthalpy H is equal to U plus P into V. We know that? That means it add some positive quantity. This is the addition of a some positive quantity. This is your addition of a some positive quantity. That means it is also a positive quantity, so it will add in this one, okay? That means this is your addition in internal energy. That means for that case, sir, H is always higher than the internal energy. H is always higher than the internal energy. That means the enthalpy column is higher value as compared to the specific internal column. Okay. So in this one there is also Hg and Hf, Ug and Uf. My dear, if there is a Hg to Ug, Pg, Vg, so this must be higher. Okay, and this must be higher. Hf is must be higher. Now in this one, this Ug is higher. In this one, this Hg is higher. See the beauty. See the beauty. This is your observation. Hg, Hf, this relation we have to know, we have understand successfully that sir, the specific enthalpy is always higher than the specific internal energy. Now, so a specific enthalpy contains Hg and Hf. Specific internal energy contains Ug and Uf. So obviously Hg is higher than the Ug, Hf is higher than the Uf. Now this is the enthalpy of a saturated gas, have a more energy as compared to enthalpy of a saturated liquid, and internal energy of a saturated gas is more than the internal energy of the saturated liquid. This is very important. Okay. Now, so which one is there? Okay. So, okay, this is okay, no problem. So Hg is 6 number column. This is your 6, and Sf is 4. Okay, no problem at all. Now, my dear, you have to select Hf. Okay, no problem. Hf, Uf. So Hg is greater than Hf, Ug is greater than Uf. Okay. So, and one thing you know that if there is a liquid, note, very important. Third point, you know, also know that. See my dear, what is the Hf? If you take Hf at the same pressure, so this is your Hf is equal to Uf plus same pressure P into Vf. My dear, the specific volume is very, very minimum. Why? Because density is very high. So this is value is very minimum. Minimum. Why? Because it is 1 by density. Density is high. So we can neglect this term. We can neglect this term. We can neglect. So if we can neglect, so approximately Hf is equal to, that means what is the enthalpy of saturated liquid is approximately equal to the enthalpy of a internal energy of a saturated liquid. This is very important observation. So my dear, Hf is little bit higher, but it may be equal. Okay, it may be equal. Okay, higher and equal. Okay. but the difference is very minimum. So if you take an HF is minimum, HF is minimum and HF is minimum as compared to HG, and HF is approximately same as UF. So in this one, HG is very maximum. In this 4 contents, this is a maximum value. This is your maximum value, and in this one, this is your minimum value. This is your minimum value, and this value and this value are approximately equal. Very little change. Okay, so first take HG. HG is the maximum in all the content. So how many table left? The table left is, okay, it will done. So the maximum one is, see this one, maximum. So the maximum 88, this 89, so this is maximum, this is maximum, this is 14, 14, 14. So this 8th column is maximum column. So it is your HG. This is your HG. Okay? HG. And my dear, this is your HG, fix. So 8th column is HG. So this is 8th column is HG. Now, HG. Okay? HG. Now, and UF is the minimum. UF is the minimum. So take UF is the minimum. So check this one. Which one value is the minimum? UF is the minimum. So this is HG. So you have to 8, 7, 5, 3. So 3 here, 5, 7. So this is a very minimum as compared to C. 3, 5. So left is 5, 3 and 7. Why? Because it is fixed. So 3, 5 and 7. Which is the minimum value? The minimum value is 3. The minimum value is 3. So this is your what? This is your what? This is your UF. So this is your UF. So 3 is your UF. Now UF is approximately UHF. See, UF is approximately HF. So this UF is approximately HF. So UF is approximately. So whose column is approximate? See, this is 88, this is 89. So we have to compare only 5 and 7. 2 is there. So 5 is 88 and this is this one. So little bit, the small deviation, this is 88, this is 89, this is 179, this is 180. So it is approximately same. So this is your HF. This is your HF. So if this is HF, so this is your HF. So this is your UF, HF, and this is your HG. So this is your UG. This is your UG. Clear? So column 3. So we have to write like that. 3 column is your UF. 4 column is your SF. 6 column 5. 5 column is your HF. 6 column is your SG. 7 column is your UG. 8th column is your HG. Very good. So you have to find, compare. So what is your answer? The specific enthalpy data. So a specific enthalpy is 5 and 8. So the answer is 5 and 8. What is the answer? 5 and 8 is the correct answer. Clear? Is there any problem? Is there any problem? Okay. Now, when the saturated liquid is at 400 degrees centigrade is throttled to 20 degrees centigrade. The second problem, when the saturated liquid at 40 degrees centigrade is throttled to 20 degrees centigrade, the quality of exit will be, what is the exit quality? That means dryness fraction. Okay. So, let's take this one. So, the throttling we know that there is a restricted passage. So, if you plot TS diagram, okay, temperature and entropy diagram. This is saturation curve, correct? This is saturation curve. Now, so in the throttling beta, what we will done in the throttling, let's suppose throttling 1 to 2. So, during 1 to 2, the pressure will drop. Throttling when there is a pressure, thank you Sandeep, thank you. The pressure will drop. Once the pressure will drop, if the pressure will drop, and the pressure will drop according to the enthalpy at inlet is approximately the same as enthalpy at exit. This is the second condition. What is the third condition? The third condition is that means it is a highly irreversible process. That means in this one, the entropy will increase. These are the some pointers which have to always remember when you start with the throttling. And if let's suppose the throttling will done from high pressure to low pressure, that means during the throttling the exit pressure must be reduced. So there is a 2 pressure limit, that means this is the pressure at which the fluid will enter, and this is the pressure at which the fluid will exit. So this is your pressure P1 and this is your pressure P2. So this pressure at the inlet of the throttle, and this pressure is the exit. This pressure is a exit from the throttling device. Now, what the question says that in the question, see beta, when the saturated liquid at 40 degrees centigrade, that means the entry is a saturated liquid. Entry is, see, when the saturated liquid at 40 degrees centigrade is throttled, that means the initial point is at saturated liquid point. And what temperature? The temperature is 40 degree. Okay. So at a 40 degree, we have all the properties. See this one, 40 degree. See this one, this is a 40 degree, and we have the property. So lower table, this is important. For the lower one is the important. Lower one is the important one, okay? So this is a 40. So we have a 40 data, 40 wali. So there is a 40, okay? So at a 40, we all the things have. So now, entry is a saturated liquid. So this is point number 1. So this point number 1 is your T saturated. And this T saturated is corresponding to the inlet of the throttling. Okay, now, very good. Now, when the throttling, the entropy will increase. So it will increase. Let's suppose this is a point number 2. So during the 1 to 2, this H1 is approximately equal to H2. H1 is approximately equal to H2. Now, beta, we have one condition. We have at a point 1. 1 is, what is the saturation condition it is given? Saturation temperature. See this one. The saturation temperature it is given 40 degrees centigrade. So this is your 40 degrees centigrade. 40 degrees centigrade. And what is the pressure? The pressure it is, what is the pressure? The pressure it is your 1554.9, 1554.9, 1554.9 kilopascal. This is the inlet condition. That means this is your throttling device. If this is your throttling device, if this is your throttling device, if this is your throttling device, this is your throttling valve. So this is your inlet 1, this is exit 2. So at a one condition it is given P1 and T1. Now it will throttle and throttle. This is your weight region. Weight region. Okay, this is approximately weight region. We have to check whether it is weight region or not. And this is your, we have to check. This is your, must be a saturated liquid. It is given. Liquid, it is given. So whether this is point number 2 or not, we have to check one. Okay. So first we have to find the dryness fraction. What is the dryness fraction at a point 2? How to find the dryness fraction? The location, we have to choose the location of 2. Location of 2 is where, which point? We don't know. Initially point we have a saturated liquid, but the final point we don't know. The final point we don't know. So for the final point, how to define the final point? While if we have to knowledge about the dryness fraction, we have to adjust the point number 2. So how to find the dryness fraction? The process 1 to 2. That means H1 is equal to H2. Now what is H1 beta? This H1 is nothing. This is your HF at temperature 40 degree. And what is the H2? This is your HF plus X2 Hg minus HF. And this is at which pressure? This is the exit pressure. Okay, this is the exit pressure. So this is at which temperature? It will throttled at, see this is given, it will throttled to, see this one, to minus 20 degree centigrade. It will throttle to minus 20. That means throttling is a minus 20 degree centigrade. It will throttle to minus 20 degree centigrade, and we have the minus 20 degree centigrade table. We have minus 20 degree centigrade table. Okay. So minus 20 we have the throttling up to a minus 20. So the throttling, this is your minus 20 degree centigrade. So all that data 40 degree centigrade, HF from the table, HF 40 degree centigrade, it is your 371.43. HF at minus 20 degree centigrade, HF at minus 20 degree centigrade we have, this is your 89.05 plus X2. Hg we have 1418. Why? Because see my dear, this is the data available. This is the data available. Hg minus 40, Hg 1418 approximately. So this is your 1418 minus Hg is, HF is 89.05. So from that one we have to calculate X2 value. What is the X2 value? The X2 value is, the X2 value is 0.212. That means there must be a dryness fraction. That means this 0.2, it is in weight region. It is in weight region. So once you have to calculate this X2, this is the condition. That means exit condition. So X2 is equal to 0.212 is your exit condition. Exit condition. So I hope you enjoy this sessions beta, and also you have to gather some questions. So this is my first classes. This is my first class of this events. That means excellent question practice. So intuitionally we have to take very intelligent but less calculation. But after the preceding classes, after the classes will going to the next classes level. So the level of the question will high and high and high. So we have to take this question, and this is the very, very, very important question. If you try the question, so you have to take this one. So this is your next question. If you have, so you have to solve it. So I give you a steam at 20 bar 300 degrees centigrade, pass through a pipe with the velocity of 100 meter per second. The steam flow the velocity at velocity flow rate. This is a flow rate is given 400. This is, I think it is given 400. This is given 400 kg per hour. Find the pipe diameter. You have to find the pipe diameter. Find the pipe diameter. So you have to find the diameter of the pipe. So what you have to calculate? First calculate the discharge. After the calculating of discharge, you have to multiply pi by 4 ds square and velocity. So first find the velocity. Okay. So I hope you enjoyed this session. Thank you.